Welcome to this session. In this session, introduce the concept of second-order linear differential equations. So we start by defining what you mean by a second-order linear differential equation, and then give some theorems related to second-order linear differential equations. So a differential equation of the form A2 of x plus A1 of x dy dx plus A0 of x y equals to f of x where A2 of x, A1 of x, A0 of x, and f of x are continuous functions. Is called a linear second-order differential equation. So let's call this one equation 1. So if f of x is equals to 0, then 1 is called homogeneous linear second-order differential equation. But when f of x is non-zero, then 1 is called non-homogeneous linear second-order ordinary differential equation. So that's how we define a second-order differential equation. So this is the main equation. So let's give a definition of what we call linearly independent functions. So let a set S have two functions, f1 of x and f2 of x. Then the set S is linearly dependent on an interval I if there exists two constants, C1 and C2, not both zero. So this is a key thing. So that C1 F1 of x plus C2 F2 of x is zero for every value of x in the interval I. Now, S is linearly dependent if there are constants C1 and C2, both zero, so that C1 F1 of x plus C2 F2 of x equals to zero for every value of x in the interval I. So dependence and independence will actually be of key interest when we'll be getting solutions of second order linear differential equations. And then there's a theorem that we call principle of superposition. Now, principle of superposition states that if you have two functions, f1 and f2, which are solutions of equation 1, so this will be reference equation. So if f1 of x and f2 of x are solutions of equation of the homogeneous ordinary differential equation y double prime plus p of x y prime plus q of x y equals to 0 on an interval I and C1 and C2 are arbitrary constants, then y equals to C1 F1 of x plus C2 F2 of x is also a solution of the same differential equation. So that's what we mean by principle of superposition. Remember, the same can be extended to higher order differential equations of the same structure. So theorem on existence of solutions. existence, and uniqueness. So suppose that P of x, Q of x, and f of x are continuous functions. On an open interval I that contains x equals to x naught, then the initial value problem y double prime plus p of x, y prime plus q of x, y equals to f of x, subject to y at x naught equals to a value a, and y prime at x naught equals to a value b. So this initial value problem has a unique solution on this interval. So next, let's define what we mean by Wronskian of a set of two functions, but the same can be extended to more than two functions. So Wronskian. So note that we are defining Wronskian of two functions, but we can have the same definition for more than two functions. So let a set S have two functions, f1 of x and f2 of x. They have two differentiable functions, f1 and f2. Then the Wronskian of S denoted by W of S is the determinant W of S is this determinant f1 of x, and then you write f2 of x. And then the second row, you define the derivatives of these functions, f prime of x, f1 prime of x, f2 prime of x. So which is the same as f1 of x times f2 prime of x minus f1 prime of x times f2 of x. So this is simply a 2 by 2 determinant. So similarly, if S is given by f1 of x, f2 of x, f3 of x, three functions, then you can as well define the Wronskian of this set as getting the determinant f1, f2, f3, And then the second row, the derivatives of these functions, f1 prime, f2 prime, f3 prime, and then third row, second derivative of f1, second derivative of f2, second derivative of f3, etc. So you can as well define the Wronskian of more than 3 functions. So let's quickly demonstrate with an example. Compute the Wronskian of each of the following. Sets of functions. So A, S has sine x and then cos x. Now here, we have Wronskian of this set with the determinant. So you have first function is sine x, and then cos x is the second one. So define the derivative of sine x, we get cosine of x. Derivative of cos, we get negative sine of x. This 2 by 2 determinant will be sine x times minus sine x. We get negative sine squared x minus cos times cos is cos squared x, which is the same as minus sine squared x plus cos squared x. Sine squared x plus cos squared x is 1, so the answer will be minus 1. B, the set is e raised power x, x, e raised power x. So here, Wronskian is a determinant e raised power x, x e raised power x, and the derivative of this is e raised power x. Derivative of this function x e raised power x, use product rule. So this is u, this is v. So u prime v plus v prime u. U prime is 1 times v, you get e raised power x. V prime is e raised power x times u, you get x e raised power x. So this will be e raised power x plus x e raised power x, which will be e raised power x, product of elements along the main diagonal, plus x e raised power x minus this product, x e raised power x multiplied by e raised power x. So which will give us e raised power x times e raised power x is e raised power 2x minus x e raised power 2x, just loss of indices, minus x e raised power 2x. Remember, this sign is plus, because here is plus. So this can easily be seen that the answer is e raised power 2x because second and third term cancels out. This cancels out. And then C, S is given by 2x, 4x. So this will be given by Wronskian of S is determinant 2x, 4x, and then the derivative is 2, derivative is 4, which will be 8x minus 8x, which is just 0. And if I say D, if the set S is given by x squared, 2x, and then e raised power x. So Wronskian of this set will be the determinant x squared 2x e raised power x. Then the second row, you get the derivative of the first row, 2x, this is 2, e raised power x. Third row, the derivative of this, we get 2, this is 0, and then this one is e raised power x. Now, these are 3 by 3 determinant. So if you remember from linear algebra, this checkerboard, it will be easier to expand either along the second column or the third row. So along the third row, you'll have these 2 times the sub-determinant, this determinant formed by deleting the column and the row. So you have 2x, 2, and then e raised power x, and then e raised power x minus, so this is 0, so there's no need of writing there, then just plus e raised power x, because already this will be 0 times the sub-determinant of 10, which is just 0. So delete this, we have x squared, and then 2x, and then 2. So it will be 2 into 2x e raised power x minus 2 e raised power x plus e raised power x into 2x squared minus 4x squared, which will be 4x e raised power x minus 4 e raised power x plus 2x squared e raised power x minus 4x squared e raised power x. So which will be 4x e raised power x minus 4 e raised power x. This will give us minus 2x squared e raised power x. So that's how we define the Wronskian of functions. So theorem, Wronskian of solutions. So consider the second order linear homogeneous equation where P and Q are continuous on an interval I. On the open interval I. So if we suppose that there are 2 solutions, y1 of x and y2 of x are solutions of this ordinary differential equation on the interval I, and if y1 of x and y2 of x are linearly dependent, then the Wronskian of y1 and y2 is 0 on I. But if y1 of x and y2 of x are linearly independent, then the Wronskian of these two functions is non-zero. For all values of x on this interval I. And usually this attests whether the two functions you get are linearly dependent or linearly independent. So this is what we have. Now, the general solution, the interest for this chapter is to find the general solution of the second order linear differential equations. So theorem, general solution. So consider the second order linear homogeneous equation y double prime plus p of x y prime plus q of x y equals to 0, where both p and q are continuous functions on an interval I. So suppose that y1 of x and y2 of x are linearly independent solutions of this ODE. On this interval I, then if capital Y is any solution of this ODE, there are constants C1 and C2 so that, or such that, this solution Y is a linear combination of these two functions, y1 and y2, for all x value in this interval. So what you're going to deal with, or what you're going to do, is to assume that the coefficient of the derivatives, second derivative, first derivative, and the function y itself are real numbers. So solution of second order linear differential, a linear homogeneous. So start with homogeneous, then an homogeneous later. Equations with constant coefficients. So differential equations with non-constant coefficients will be dealt with when we are discussing about series solution of differential equation. But for start, we'll assume that all the coefficients are real numbers or simply constants. So we say that a differential equation of the form a2 of x dy d squared y dx squared plus a1 of x dy dx plus a naught of x y equals to f of x is what we call a second order linear differential equation. So we are going to fix, let a2 of x, let's call it a, let a1 of x, let it be b, let a naught of x, let it be c, and for homogeneous, then right-hand side is 0. So that we have a d squared y dx squared plus b dy dx plus c y equals to 0. So, or is the same thing as writing a y double prime plus b y prime plus cy equals to 0. So this is the kind of the questions that you are going to be solving in this chapter. So the question is, how do solutions of such equations look like? So let's call this one question 1. So our objective to find solution of this equation 1. Now we'll make an assumption that the solution for this equation takes the form y equals to e raised power rt, rx, not rt, because we're using x as a variable. Let's assume that the solution is given by e raised power rx for some value or values of r. Now, if y equals to e raised power rx is a solution, and because we have a first derivative and second derivative, then it means that if we differentiate the function once and then twice and replace into the equation 1, then the left-hand side should simplify to 0. So given y equals to e raised power rx, then y prime, which is dy dx, using chain rule, differentiating this one. Remember, r is a constant, so differentiating this with respect to x, we get r e raised power rx, and the second derivative means we differentiate this first derivative, we get r squared e raised power r x. So let's call this one 2. Now substituting 2 in 1, we get, so where the second derivative will be replaced by r squared e raised power rx, and then remember the coefficient is a, and then b times the first derivative plus c times the function y equals to 0. And then with this equation, we realize that left-hand side e raised to power rx is common, so we can have ar squared plus br plus c into e raised to power rx equals to 0. So there's a product of two values giving us 0, which means that any of the two values is 0. But then we know that any exponential function can never attain a value 0. So since e raised to power rx can never be 0, then this implies ar squared plus br plus c is the only possibility for being 0 to make that equation be true. Now, solving this by quadratic formula, we get r is minus b plus or minus square root b squared minus 4ac divided by 2a. And with this quadratic solution, or this quadratic equation, we know that there are three possibilities. So first possibility is having distinct roots. So three cases to consider. So case one, distinct real roots for R. This means that then B minus 4AC is positive. It's really positive. So then, actually, this is the case when B squared minus 4AC is positive. So let R1 and R2 be the real roots of, let me call this equation 3. Of equation 3, so if or since we have said so R1 and R2 are distinct, or when R1 and R2 are distinct, then the general solution of A y double prime plus B y prime plus C equals to 0 is, by superposition principle, y of x is given by C1 e raised to power R1x plus C2 e raised to power R2x. This is how the solution looks like. Case 2, real and repeated roots. So this is when the discriminant b squared minus 4ac is equals to 0. So let R be equals to R1, R2 be the real, the repeated solution of this quadratic equation, the so-called the characteristic equation, then a general solution of this equation is of the form y of x equals to c1 e raised power r x plus c2x e raised power r x. So you multiply this second one by x. And then the last case is when we have complex roots. There's 3 complex conjugate roots. This happens when b squared minus 4ac is negative. So let R1 be alpha plus beta I and R2 be alpha minus beta I. Where alpha and beta, so that beta is not 0, are real numbers. Be the solution of the characteristic equation a r squared plus br plus c equals to 0. So a general solution of the equation ay double prime plus by prime plus cy equals to 0 is of the form y of x equals to c1 e raised power alpha x cosine of beta x plus c2 e raised power alpha x sine beta x, which can be written as e raised power alpha x into c1 cosine of beta x plus c2 sine of beta x. So the next session will be demonstrating how to get solutions to such kind of equations. Thank you.